Good morning, friends. Since its emergence in late 18th century, steel structures are being used for various reasons and purposes. Till the beginning of 20th century, steel structures became popular just because of use in the military purposes. We all know how the bold experiments by visionaries created iconic structures like Eiffel Tower, Brooklyn Bridge, Sydney Harbour Bridge, and so on and so forth. With the beginning of the computational design or parametric design, the designers have got a whole new architectural vocabulary of concepts and ideas. Today we are going to witness this paradigm shift in the use of steel by the young visionaries. I'll start with Sujay. Sujay, can you start your presentation, please?
Thanks, Vivek. Morning to all of you. Just trying to share my screen. Give me a second. Yeah, so morning all. This is, essentially the whole idea of, using steel is to not just have it as another structural alternative to concrete, but the point behind some of the projects that we do is to actually celebrate steel. So, which is what I've been coining this as for a long time. And what I mean by celebrating steel is to make it visible, to make it an integral part of the design, to give it its position and place that it deserves as a design element. So the project that we are going to talk about today or present to you from Opus essentially is a commercial space that we have done in Bangalore, an area called Kalyan Nagar. All right, so this is a building. It's a very small commercial building in the hub, in a very commercial hub called Kalyan Nagar in Bangalore, where there are other contemporary buildings. When the client initially came to us, they wanted me or us to start basically look at a very different approach to a commercial building. The typical column structure with a ACP or a glass facade was not something that they were looking out for. I have always wanted, and I've always played a lot with steel, and steel seems to be my favorite material to go to. I proposed, I checked with them if they were okay with steel. They seemed to be, and this was the first proposal that we gave to them. So essentially, as you see here, it is an exoskeletal diagrid. Our experiment was to, use this as the facade, use this as an elevational element, as an external feature, and not hide it behind a glass curtain or any other kind of a facade, and to actually celebrate steel, like I mentioned. So essentially, yeah, this is what a building looks like. You would typically see a diagrid which is spans the height of one floor. So this is a 5-floor structure. There's a basement, and then we have 5 upper floors. This being having a light roof on top. There's a light sloping roof which slopes inwards. The whole premise of this lied around the fact that we wanted to experiment with the diagrid and not use a typical column and beam kind of a structure. Essentially, initially we made the diagrid, and later on came up with the concept that why not expose the diagrid, expose the structure, and hence give it a very unique feature. This is a shot of the interiors. Interestingly, we had one client who wanted to rent this space, who came into the space, and he was looking around, and I happened to be there. I asked him, what are you looking out for? So he said, I was looking for columns. He said, there are no columns? So I said, no, that the tubes that you see outside are actually holding the building up. And I still remember the look on his face, and I gave him a small lecture about what diagrids were and how they worked. So essentially, yeah, so this is an external lattice which acts like an exoskeleton. Essentially, it means that there is no skeletal framework inside, and the skin of the building is what actually holds it up. We have a lone central column that you saw in the previous image, which essentially was used to reduce the beam depth here, to reduce the span along the central axis. But essentially here the exoskeleton is what is holding up this entire building. And if you can see from this graphic below, the the green part is actually the concrete base, which is the basement, and the core, which has a small lift lobby, toilets, and the staircase. So that's made in concrete. And the rest of the floor plate is entirely made in steel. And of course, I mean, I'll not delve into the aspect of how triangles are the strongest simple element and all of that. I think that's quite known at this point in time. Today's presentation is largely around this particular detail, which is the node detail. If you see the elevation, we had to resolve the junctions of all of these struts or tube elements. And initially when we came up with the idea of the diagrid, we quickly realized that the god lied in the details of this particular node. So then there were many iterations done, many concepts that were evolved as to how we would go ahead and design this detail. Although you would just imagine that these are 6 tubes that come in one place and they're welded together, when you actually work out an algorithm of how you would construct this, it's not so easy. So today's presentation largely revolves around how we went ahead with the design details. These are some of the drawings that were given out of our office, some of my initial sketches when we conceptualized how the glazing and this external diagrid as well as the beam structures interfaced, and how we would make it waterproof, and how structurally stable this whole thing would be. I'll quickly go on to some site images, which kind of gives you an overlay as to how this was constructed. Some of the joints between the beams here. This is the joint between the central circular column and the beams across. Some more here. This you see the diagrid under construction. 2 floors here with the beams being overlaid. This would be the steel roof, the inward sloping roof that we have on the upper level. Now, essentially, I chose this small project because although it was small, there was a lot of steel elements, and like I said, we have used the steel as a hero here in order to achieve the elevation or the design that we wanted to. Here you see how the slab reinforcement has been welded to the peripheral I section beams. This is where and this was a regular, we had not used decking for cost purposes. To bring that down, we had a regular centering mechanism for the slabs. And so basically there are regular concrete slabs which are cast between the beams, between the steel beams, and then de-shuttered. So this was another element which makes it a composite structure. Yeah, so what I'm going to talk about is essentially these nodes. Today you see this in the image. We had to use cranes in order to put up elements here. The biggest challenge was I wanted these nodes and these tubes or these struts to seamlessly join into each other. Typically, when we see steel construction, you see a lot of cleat plates. You see a lot of plates being welded on top of joints between 2 elements, where the aesthetic of that was that joint would be compromised. So the idea here was to take this detail this joint in such a way that none of those external cleat plates or stiffener plates would be visible, and all of that would be concealed, which meant that we had to use a stiffener plate, but it had to be inside the tube and not from outside. That one simple requirement complicated this entire construction quite a lot, and we had to still deliver. Also, because this is a diagrid and it's a very geometric figure, if there is, let's say at the ground level, there is a 1 degree shift in the angle of this element, this would result in 100 to 150 mm error at the topmost level or at the terrace level, and hence the precision on this build had to be very precise. We had to have a lot of precision so that there were no errors geometrically. So it was imperative that these nodes had to be prefabricated in a shop floor with the precise angle, and then brought to site and installed at the precise location. So although this is easy to say, but at site there were a huge number of challenges. So here you see that there is a fabricated node being installed along with the rest of the tubing. You see the welders welding and plug welding the various joists and the beams into a node. You see the process of plug welding. You can also see plugs here which are yet to be welded. You see a plug hole here. I'll detail this junction out. So essentially what happens is, once these junctions nodes are put in their place, it is let's say these 3 nodes in question, introducing these struts in the middle with just about 6 mm to 8 mm of a gap between the two for us to fill the weld with was a challenge. So this is like you had to introduce the sleeve from it had to have a sleeve inside, but you couldn't, how should I say, put the tube onto the sleeve. This this tube had to go between the 2 nodes. So this was the detail that we did. This is like a quick stop animation that will help you explain. We had the red color here is a sleeve that goes into the strut, which is a blue tube here. This is a prefabricated node that was already there. So how we went about it is, I'll show you in this animation. First, the sleeve goes into the tube. What we then do is we've slide the tube, so the sleeve into the tube fully. Then there is this small peg that is welded in place to hold that sleeve in place. Eventually we also have a stopper peg which is introduced inside the node at that location, so it has gone there. And then we introduce the tube onto the correct location, aligned it, and then slowly removed this peg. So moment we release this peg with some effort, because we had this slot at an angle, we could force this inner tube down to rest onto the stopper peg that we had. So this way the sleeve got introduced inside the tubing, and it became an integral part of the node and the strut. And eventually all the welds, which is the plug weld, the slot here for the plug weld and the tubing joint with an 8 mm fillet, were welded. Okay, we had a prefabricated capping for better aesthetics, because we had to have a lot of external welding which we couldn't grind onto this for structural reasons. We had a cap, so this took care of the aesthetic. This was made with a 5 mm sheet, and then this was superimposed on that particular joint, essentially to then give us a very seamless and how should I say, external a very clean joint, if you like, which had a perfect aesthetic. So this is how it ultimately finished. So although it's a very small project, and even from a tonnage point of view or a square footage point of view, we are happy that Mr. Devaya, who is a client, gave us an opportunity to play with steel. Also happy that our consultants and the contractors, by the way, this entire thing has been erected by an ordinary fabricator. We had immense detailing that was done, and these guys are good at what they do. And once they figured one node out, it was a matter of repetitive production. And in fact, the detail was made in such a way that it was repetitive. And once they understood the concept, they could go on and erect the rest of the structure, having understood the fundamentals as to how this had to go in. So in my 10 minutes, I guess this is all I have for you today. And it was nice being here. And thanks for having me.
Thank you, Sujay. Wonderful presentation. My compliments.
Thank you, sir.